Okay. So we've discussed so far in these last couple sections the basic ideas of integration, connecting it to a simple area formula along with a limit process. That's where we spent the majority of our time the last couple days. We've been reviewing those ideas over and over again. Today, we're going to look at a standard rule from derivatives that has an opposite we haven't talked about in integration. So that rule is the chain rule. So back when we were doing derivatives, we'd have the rule that d dx of a function inside of another function is equal to f prime g of x times g prime of x. Your basic chain rule. Well, this is one of the few rules that actually has a natural opposite when it comes to these particular functions. There is what's referred to as the U substitution rule, which will allow us to undo a chain rule in integration. It actually goes based on a theorem. That theorem is theorem 413. Theorem 413 states the integral from f of g of x times g prime of x is equal to capital F of g of x plus c. Which, if you look at it, it's just basically the chain rule. It's written in reverse. What's important to note about this function is that there's two main components to it. There is an interior function, g of x, which is inside another function, and whose derivative is outside. So if you happen to see that a function has a derivative inside of that function, it's probably a good indication you're going to do what's called U substitution. Why is it called U substitution? Because the most common way to write this form is not with g's, but with u's. Integral little f of u du is equal to capital F of u plus c. Where u can be a function, could be a constant, could be anything. Easiest way to understand this is with some examples. And I got a lot today. So, start on the first one. Integral of x squared plus 1 to the fourth power times 2x dx. These first couple will be very straightforward, very simple. Where it's possible you could solve it without using this rule, but using this rule makes it convenient. So, let's look at our example. The integral of x squared plus 1 to the fourth power times 2x dx. Now, there is a straightforward process that we can use. It's about 6 steps long. I will showcase how the process is written out. But for now, we're just going to kind of work our way through it. How you know you're going to use this rule is if you see an interior function whose derivative is on the outside of the function. This is a clear indication that you should probably do some kind of U substitution. Again, where the actual function is inside another function and its derivative exists outside of that function. In this case, what is going to U substitution? I'm going to create a variable u, which is going to make it equal to x squared plus 1. Now, in order to perform a change of variables, you must actually change every piece of this function into the new variable. Meaning every x that's in this problem has to somehow be converted into some kind of u. That's the x here, the x there, and the dx over there. The best way to convert the u and to get rid of the x is by actually taking the derivative over here. Once you've established what your u is going to be, take the derivative and see what happens. This first piece will be du, because it represents the change of the function u. The derivative of x squared would be, of course, 2x, with the change in x happening. Now it's common to write dx as 1 because usually we're trying to simplify as far as possible, but in this case this is actually really beneficial because in this case if dx still exists we can perform a substitution. So your goal becomes to get everything in this problem related to our new variable u. So notice how we can do that. Now our integral would be the integral of u to the 4th power times 2x dx is equal to du. So this piece is du. This integral now is just a power rule problem. But it's a power rule problem with a u in it. It doesn't change much. But notice that every x that was in the problem is now replaced with some version of u based upon the x function. So the du is a derivative of an x function. From here, we just simply take our function and integrate it. So this becomes 1/5 u to the 5th power plus c. And as common in mathematics, if we start with a function in terms of x, we should probably end with a function in terms of x. So we'll make a segment substitution here, turning this function relating to u back into a function relating to x. Another.
The times We'll have to do the times
Remember, when you integrate the du and the integration symbol are connected to each other. So if you get rid of the integral, you get rid of the du as well. As soon as we get rid of the dx before.
So it'd just be 1.
Now, I can verify this is correct by verifying that the derivative and the integral cancel using the fundamental theorem of calculus. So that's what I'm going to do. I want to verify that this statement is the derivative of that statement. And therefore show these are exactly the same. So I take the derivative of this function. To do so, I'm going to have to use the chain rule. So I take this, I multiply by the power, so I do 1/5 times the power, subtract 1 from the power, times derivative of the inside. Derivative of the inside would be just 2x. The derivative of c would be 0. The 1/5 and the 5 cancel. Then we just x squared plus 1 to the 4th power times 2x. And the 0 goes away. They match. This must be right. Again, the clear indication that you're going to be using this kind of rule is this kind of function. Now, in this example, it is entirely conceivable we could have just simplified this manually. Using like Pascal's triangle, or even just FOIL it a bunch of times. We could have done this by hand, is what I'm trying to say. It's just, this is much simpler to do if you understand the concept of a u substitution, where you take the function written as a term of x and rewrite it in terms of a new variable which we call u. Why u substitution? Well, you could use any variable. U is just kind of really common. I've never seen a math textbook that use anything else. Oh. Again, the key thing you want to look for, an interior function with an exterior piece that is the derivative of that function. That's a clear indication you're going to use this step, this process. Here we go. Integral. This is one that you cannot solve with traditional techniques. So the last one you could have if you were willing to FOIL it all the way out. This one, not so much. So again, the idea of this rule, like many of the things we talked about, is to expand the possibilities of what we can do. We have our basic rules, which allow us to take these functions and simplify them by hand. This one allows us to also simplify it by hand using a more advanced rule, u substitution, theorem 413. So, first, how do we know this is a good rule to use? We have an interior function whose derivative is outside of the function. This is a clear indication we should probably approach it this way. Next piece. Should I talk about it all the time?
Yes.
Dear Lord.
That's why we love it.
Okay. So, what I'm going to do is I'm going to fashion a function which I'm going to call u, equal to the interior or nasty part of this function.
Yes,
Now, here's the thing, like, if you choose the wrong u, you'll often end up with a function that isn't very much nicer, or isn't solvable by traditional rules. Example, what if I just made my u the x cubed? Well, that would actually work, because then you'd have u plus 7, and on the outside would disappear, because the square root and the x would end up canceling with the du. The problem is you're left with a square root, and it's not solvable by traditional techniques. And so your goal should be a couple things. When you're finished, you want to have a function that is integratable. So if you pick a u and it's not integratable at the end, you probably picked the wrong u. So I picked this to be my u for two reasons. One, this function is inside my big picture. And its derivative, du, is outside of this function, 3x squared dx. What I can do now is do a simple substitution. My dx and 3x squared are right here. I take these two pieces and replace them with a single du. I take this piece and replace it with u. So I end up with the integral, the square root of u du. A function which is significantly easier to solve. The other one is actually impossible to solve by standard techniques. It's a product of two functions, neither of which are simplifiable, so it's impossible to solve with those traditional techniques. This, however, is solvable. Again, I convert this into a power, and then apply the power rule. The power rule would state, add 1 to the power, divide by the new power. So u to the 3 halves over 3 halves plus c. Last thing, if I started my function in terms of u, I should end my function in terms of u. So, x cubed plus 7 to 3 halves plus c.
Do we have to write it like we would the original function in square root form?
I would prefer it. So I would make one simplification here. So first I'm going to fix this. Dividing by 3 halves is the same as multiplying by 2/3. This becomes 2 over 3 times. Okay, the x cubed plus 7 to the 3 halves power would be the square root of x cubed plus 7 cubed. Or you can put cube on the inside as long as it's applied the whole thing. There's a lot of different ways you can write it. Just make sure, since it is an indefinite integral, you must include the constant of integration, c. You can also, on some occasions, leave it that way. If I'm going to check my work, you better believe I want it in that other form. It's much easier to check my work from here, which I will do now. The fundamental theorem of calculus says integration and derivatives are antithetical, meaning if I have the derivative, I should be able to integrate to determine that they're the same. And if I have the integral, I should be able to differentiate to determine they're the same. If I differentiate this function, what happens? X cubed plus 7 to 3 halves power, all over 3 halves. And I'm taking the derivative. Well, we would take this function, you'd multiply by the power, so 3 halves move up front, subtract 1 from the power, and then times by the derivative of the inside. Derivative of the inside would be 3x squared. From here, 3x and 3x cancel, and this is my original function. So the fundamental theorem of calculus holds. They are in fact opposites. The trick with u substitution is two parts. Number one, can you spot the u? And number two, can you substitute the du? And you simplify the function to make it just a little nicer. And again, you know you're doing it along the right path if you end up with a solution that is easily integratable. That's integratable. Standard rules for power rules. Anything else? We need to reconsider what steps we took. Make sure we took them correctly or have the right pieces of that function. Alright, one more. So one that was solvable by the traditional techniques, just not really want to solve it that way. One that's not solvable at all. Let's look at a trick one. Good? Integral of secant squared x times tangent of x plus 4 dx. The trick is to spot your u and du. Because again, if you can spot the u and the du, then this problem is a simple matter of can you make the substitution work through algebra. So, looking at this problem, I have some options for what I could make my u. One of those options is the best. Just a showcase, like, you can perform a u substitution for anything. Anything could be your u. In this problem, I could make just the x into u. It would be a terrible idea. Because all I would do is just replace every x with a u. But it's still a u substitution. I could replace the secant with u. I could replace secant squared with u. I could replace the tangent with u. I could take the tangent plus 4 as the u. I could take this entire thing and try to make it into a u. I have lots and lots and lots of options. But which one's the best one? Tangent squared plus, or tangent plus 4. Yes. U is equal to tangent plus 4. Why is it the best one?
Because the outside are the derivative.
That's right. So, the derivative of tangent of x plus 4 is secant squared of x dx. So we're changing x at this point. So, what I can now do is, everywhere there is a secant squared x dx, which is right here, I can replace with just du. Meaning I now have the integral of u du. Now, if I had just chosen tangent, I'm actually still able to do this problem. It looks a little different. I'll show you in a second what it looks like. Alright, ready? Let's integrate. Once you've got your function rewritten, it's just a matter of integrating. So I use power rule. This would become u squared over 2 plus c. I don't like having a function in a different form than what I started with. So I take the u that I used to have as tangent of x plus 4. I put it back in. Tangent of x plus 4 squared over 2 plus c. And again, I can verify this is correct using the fundamental theorem of calculus. I use a chain rule, so I multiply the 2 to the front, the 2 to cancel. I then take the derivative of the inside, derivative of tangent of x plus 4. Derivative of tangent is secant squared, derivative of 4 is 0. This still holds with the first fundamental theorem of calculus. Woo! Yay! Now, this is a rare problem where there's actually more than one equitable u, so I want to showcase that too. In this case, that's why I hate that. Let's assume, instead of using tangent of x plus 4, I just try tangent of x. Well, the derivative of tangent of x would be secant squared x dx. Again, normally the dx goes away, but because I'm dealing with two variables, I'm going to keep the dx in there so it stays in the problem. Well, what happens over here? I have the integral. Again, the secant squared and the dx are right here, replaced with du. But now tangent is our u, so we end up with u plus 4 right here instead. When I integrate this function, something unique happens. So integrate, I end up with u squared over 2 plus 4u plus c. Resubstitute back in. Everywhere there used to be a u, I replace back with tangent of x. I end up with tangent of x squared over 2 plus 4 tangent of x plus c. This is the same as the other one. It requires some simplification to show that's true, but it is the exact same as the other function. Questions? Cool. Welcome to U substitution. It's the most fun part about integration. Well, most fun part you typically learn about in my class. Yep. Let's look at a couple where the derivative isn't necessarily exactly in the problem. Look at this one. Again, this is one we could do by hand, but in this case, it's not a great sign to do so. Integral of x squared times x cubed plus 1 to the fifth power. Well, there's a slight problem. The derivative is not exactly in this problem if I choose the correct u. So, based upon the previous couple of examples, where are we leaning in terms of our u? What do we think our u should be?
Based on the last example, is x cubed plus 1.
Yeah, right?
But there could be a
Actually, this is the best one.
Oh, it is? Okay.
Yep.
Yes.
But there's a problem.
Dang.
Du would equal 3x squared dx. What's the problem?
You only forgot what it is.
3. I don't have 3x squared, I just have x squared. Well, now it's time to pull out the algebra brain. I don't want 3x squared dx. I want just x squared dx. How would I get rid of the 3? I could divide both sides by 3. That's right. Now, I could write it as du over 3. I'm going to be that guy and do 1/3 du. Okay, everywhere I see an x squared dx, I now replace with 1/3 du. So I have an x squared, I have a dx, I replace that with 1/3 du. I have an x cubed plus 1, that is u, to the fifth power. Now, according to a theorem, that 1/3 is a constant. I can actually pull that out to the front. And now I have a power rule problem. So even though the derivative was not exactly in the problem, we can algebraically get it into the problem. This is fine as long as it's only separated by a multiple of a constant. Just rearrange, use an algebraic manipulation to get that number to be the right number. Speaking of which, let's finish this. And as the previous one, I will take the derivative to see if they actually do match. So let's do this. The 1/3 is just a 1/3. U to the 5th power would become u to the 6th over 6 plus c. Now the 3 and the 6 become an 18. And the u is x cubed plus 1. Plus c. Don't forget your c in this section. We're going back to indefinite integrals. The constant of integration must be there, plus c. So again, in this particular function, the u did not exactly match with the du into the function. But we got it to match by using algebraic manipulation to reorganize some of our pieces. A common approach. All right, let's verify these are the same. So I propose to you that this is the derivative of that function. Let's verify that. I take x cubed plus 1 to the 6th power over 18 plus c. I'm going to take this function and do the derivative. Well, first of all, the c will disappear, as it should. Now what happens? Well, power rule. So the 6 would move out front. Subtract 1 from the power, making it a 5. Times the derivative of the inside, because it's chain rule. They become 3x squared. All over still 18. The 6, the 3, both cancel with the 18, leaving me with the exact same function as before. Look at how good we are. So again, algebraic manipulation allows me to take this function and solve it into a different form, as long as at least most of the derivative is in the problem. Now, there are still some functions we cannot solve without some other piece. Example, in this original problem, if this was, say, that, not solvable anymore. It's just not solvable. Part of the derivative has to appear in the problem, the part that deals with the variable. Otherwise, you end up having some issues. Now, there are some workarounds with some really fun little consequences. But in general, you want to look for a u where the du is in the problem in some form or another. Another, using this exact same trick. Ooh, I like this one. Integral of the square root of 2x minus 1 dx. I'll give you guys 4 minutes of time. Tell me what the integral of this function is. And do not forget your plus c. 4 minutes of time. As you're doing that, I'm going to put my steps on the board that I recommend to you. These are in the textbook on page, I think it's 306. Not sure, 304.
one for time. So we need to calculate the pass. Just dividing the answers the same thing all the time. See, like sometimes we can talk about one plus like two thirds.
So, yeah, no problem. No, it's fine.
I would accept either of those answers.
What if I divide it off? Not have one third, but just go underneath it.
The same thing, right?
Yeah.
I prefer to leave the 1/3 and the fractions out front. Just because eventually we'll talk about double integrals, just like we have double derivatives. Jesus won't save you from that. Because integration isn't a sin.
Just like not agree.
Controversial, yeah. Love by the hat, by the way, Katie. It's a beautiful hat. It's all sparkly. Questions? Comments? Concerns? Here are 6 steps. Step 1. Make sure to be consciously choosing a u with the du in mind. What is the du going to be? Does it exist in the problem? Next, solve for du using that integration technique. Next step, rewrite the entire function in terms of u and du. Finally, integrate that function, then rewrite it back in terms of x and check using the second fundamental theorem of calculus. I'm sorry, the first and the second. Long day. All right. I'm going to put one more example on the board. You'll have the remainder of class to figure it out. That's what you think. All right. It'll look a little similar, with one small exception. You have the remainder of class. It's like 13 and a half minutes.
Jeez.
Oh, man.
If you can figure out the trick, you'll be done in less than 5. Because there is a specific trick here that has to be done, and we haven't discussed.
Wow. What would it mean, aren't you?
Can't we just do it like normally?
Nope.
Put the x back in.
If you try to put the x back in, then when you try to do a u substitution, the derivative is not on the outside.
What if I don't use the u substitution?
It can't be solved without a u substitution. Because you have is 3x to the third minus x squared, square rooted, which cannot then be integrated.
Got it, okay.
Hey, you asked. I promise to give a full and complete answer.
Those that pick the same name.
First step is correct. So, you have correctly chosen your u. What's step 2? Uh-huh. What is the derivative? Okay. You have quickly completed step 2. Where you're going to have trouble is right here, step 3. Rewrite in terms of u into u. What an interesting, unique concept there. See? How interesting. Might even work. Never know. I certainly wouldn't know.
Yes, you would.
Would you like to say that again, Cindy? Yeah, we could solve for x. We have a function, right? U is equal to 2x minus 1. But that's not the only thing we have. I could add 1 to both sides. And divide both sides by 2. Remember, I have to write the entire function in terms of u and du. Now what happens? Integral. I would use this one. It's still true. There's nothing wrong with it. And it's much easier to solve than the other one. Right?
U over 2 times U plus 1 over 2. Times the square root of U.
Congratulations. Always wanted to do that. Usually I make it as a joke, like, you get a cookie. Actually, that could be this time. Usually. Good story. Well, if you would have gotten it, then you would have gotten it.
I know that. I don't like those cookies, so.
I'm sorry.
Fine.
Okay, even still, like, this form is still not great to solve this problem. So the next step is really key here. We have done the first 3 steps together correctly. Now, Sydney, fantastic suggestion. Okay? Ricky, great execution on that suggestion. Okay? Both these really good. But now, this is where our algebra skills have to be on point because this still is not integratable unless we fix some things. So I'm going to fix some things real quick. I'm going to take these 2's in the bottom. They're constants. I'm going to move them out. 2 times 2 would be 4, so I'm going to put a 1/4 out front. Integral. Leaving me with the square root of u times u plus 1 du. That's a terrible one. Yep, you gotta distribute that square root of u to each piece. So this becomes the integral, the 1/4 out front, of the square root of u times u is what? So,
U squared.
yes, put that in a better form. U squared u is correct. There's a way to simplify that algebraically with power rules. U to the 3/2. Now we got an integral with 2 pieces that are power ruled. So we can easily do this power rule. Let's do it. 1/4 stays up front times. We add 1 to the power, so u to the 5/2. Divide by any power, 5/2. Plus, add 1 to the power, so u to the 3/2. Over, divide by any power.
Yes.
Plus C. All right. I'll simplify what I can inside and then worry about that 1/4 afterwards. 1/4? So dividing is the same as multiplying by the reciprocal. So this becomes 2/5 e to the 5/2 plus 2/3 e to the 3/2 plus C. And now we can distribute that 1/4, and everywhere there's a u, we replace with 2x minus 1. Let's do it. Distribute the 1/4. This become 1/10. This should become 1/6. Instead of u, 2x minus 1. The 5/2 power. 2x minus 1. The 3/2 power. Plus C. I consider that a fine solution. Just fine.
Alright, Nick, do the last step.
Last step. And this one is it's pretty rough. There's not a good way to get this to go back to the original function without doing some real fun simplification at the end. I have 5 minutes. I'll do it. So, the first couple steps are pretty easy. Taking the derivative and just simplifying it back to the original form is kind of fun. Here we go.
Like, non-do this right.
Distribute.
Did you shoot the 1/4?
Yeah, you
The
distributed
1/4. Oh,
You
I
distributed
forgot
to
about
the
the
first
1/4.
There you go.
Oh, you did the 1/10.
Alright, I'll do this part first. This becomes, let's see, 1/10 times 5/2 2x minus 1 to the 3/2 times 2 plus 1/6 times 3/2 2x minus 1 to the 1/2 times 2. Alright. The 5 and the 10 are going to cancel, leaving me a 2 on bottom. The 3 and the 6 are going to cancel, leaving me a 2 on bottom. The 2 and the 2 are going to cancel, leaving me just a 2 on the bottom. Two and the 2 are going to cancel, leaving me just a 2 on the bottom. At this point, I'm going to actually use a property of algebra, which allows me to rewrite a function by factoring something out. There we go. So I pull the 1/2 out, and I'm going to pull a 2x minus 1 to the 1/2 out. Now, if I pull that 2x minus 1 to the 1/2 power, this comes from college algebra. When I do that, the first term will be 2x minus 1, plus the second term will be a 1. Negative 1 positive 1 cancel. And then what I'm left with is 2x, 1/2, 2x minus 1, the 1/2. The 1/2 and the 2 cancel. You better believe this seems what I with. You see that? Mental strong. Yeah, if you stop right here, it doesn't look at all like it, right? It's only after you fully simplify that you realize, yes, they are in fact the same. But if you graph them both, you'd realize instantly they were the same because they are the same. That's just how it works. So,
I'm just joking.
I'll be posting the homework hopefully this afternoon. Don't forget homework from last week is due tonight. Yes.
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 To go.
And we all started working on it and have it mainly finished and we're ready to go on this assignment. 1 through 95 odds will be due next Monday. I'll let you know this is the second to last section in the chapter.
Nice.
I'm just saying.
Tomorrow, we're going to go through some more examples, especially this kind. This kind can be rough. We're going to work through some textbook problems, like the evens. And we'll talk about the 3 theorems remaining in the chapter. That's it.
You want to see the house I'm building?